Here I will look at an example in convergence of a certain series, power series. So let's consider the power series defined by x to the power n divided by n, like this one, right? So for any x, we look at the number f of x, which is the infinite sum on the right hand side. Well, a legitimate question is, what is the domain, right, of this function, right? For any x, we can define the sum of n equals 1 to infinity of x to the power n divided by n, but not always this will lead to convergence. So for what x's is this a justifiable formula, right? So for what x does this infinite sum on the right hand side define a real number? Okay, so the answer is that we might use, we want to look at all x's for which the power series converges, right? So that will be the domain of this function. Okay, we're going to use the ratio test. We've seen this before. So the ratio test applied to the power series is that we define a sequence by an is equal to x to the power n divided by n. And then we're going to look at the limit of the absolute value of an plus 1 divided by an. And if we do so, we get the following: the limit of n to infinity of this fraction, right? So we just plug in the formula that we have for an, and you already see that it simplifies, right? So x to the power n plus 1 divided by xn is the absolute value of x, and we get n divided by n plus 1 as the constant, right? So now we take the limit for n to infinity, but then we see that the limit for n divided by n plus 1 is 1. So we get, as a limit, we get x, right? So we see that we get convergence on the basis of the ratio test. We can conclude that it converges if only x is smaller than 1 in absolute value, right? So that's exactly what the ratio test says. Okay, now we're going to look at two specific values. We're going to try to expand the interval minus 1, 1 to the boundary points. So let's have a look at x equal 1, right? So for x equal 1, what kind of series do we obtain there? Well, we just plug in our x, we get the series x to the power n divided by n is the series, the sum of n equals 1 to infinity over 1 over n, which is the well-known harmonic series, which is divergent, right? Okay, but the previous theorem, we've shown that when for some x the series is diverging, then we also get divergence for x's in absolute value larger than the value. So we also see that the above series diverges, power series diverges if only x in absolute value is larger than 1. Okay, but still there's a value where the absolute value of x equals 1, and that is for x equal minus 1. So that's the case we treat separately. So now assume x is equal to minus 1. Okay, what kind of series do we obtain there? Well, we take the sum of n equals 1 to infinity, and now powers of x will lead to minus 1 to powers of minus 1. So we get n equal 1 to infinity minus 1 to the power n divided by n. Yeah, but this is also an alternating series, right? So where the underlying sequence 1 over n is monotonically decreasing with limit 0. So we know that this is as a result of the alternating series theorem. We know that this one is convergent. So now we have a full-fledged answer, so we can say that the function f is only defined for values in the interval closed left closed interval -1, right open 1.